So I know that we're behind schedule, so we're going to try and like pick up the pace a little bit. So loops are a programming structure which allows us to repeat a command or list of commands for each item in the list. They are good for productivity because instead of having to write, the same command a bunch of times for a bunch of different files, for example, you can just set this loop, go through these files, and then it'll run a specific operation on all those files. So I think this is the example that they give us here. Suppose you have several hundred genome data files named Basilisk, Minotaur, Unicorn, and we're going to jump into the creatures directory. So, yep, I'll jump into creatures, cd creatures. We've got Basilisk, Minotaur, and Unicorn. And so if we want to look at the structure of these files, we can look at the top 5 lines. So it's got common name, classification, updated, and then its genome information as well. So if we want to, for example, just get the classification for each species, we'd have to take the second line. So the way that we would do this is we'd go for thing in list of things, do operation on the thing, and that's it. So for this example, we would do for file name in Basilisk, Minotaur, or Unicorn. We are going to do head -n, so the n flag of 2, on the file name that we're currently looking at. And then from the top 2 entries, we want the bottom one. So then we pipe that into tail, and that gives us just this bottom output. So I'll copy that actually to show you guys. Oops. That didn't quite work. So that copies all of these. One moment. And that just gives us, the classifications. So this is, just letting you guys know that you can use semicolons to separate 2 commands written on a single line. And when the shell sees the keyword for, it knows to repeat a command or group of commands once for each item in this list. So it'll keep running through those files that we assigned the for loop to. So just looking at this, I think what we would like to do is just jump onto this section here where when using variables, it is also possible to put the names into curly brackets to clearly delimit the variable names, file name, and it's equivalent to file name in those curly brackets. But it is different from file name because you want to keep those variables consistent. So we have called the variable in this loop file name in order to make its purpose clear for human readers. The shell doesn't care what the variable is called. So if we called the loop as for x in these files, this command would pretty much give you the same thing, as well as if you named it, for example, temperature for each of these files, temperature. They work exactly the same, but it's going to get really confusing if you guys aren't naming your variables in a useful human readable way. So you'll come back, you'll see temperature, you'll be like, what the heck? Why is it giving me classifications? Yep, so this is just that point. So now we're going to look at some variables. So for this exercise, we'll go to molecules. So cd --, ls cd molecules ls. Let me just check. Aditya, if you're here, just let me know if anyone has any questions, because I'll have to keep moving back and forth.
Yeah, sure. I'll take a look at the chat.
Great, thank you. So yep, we do see that. So what would be the output for the following code for data file in PDB do ls.pdb? So for the data file for all of the PDBs, we're going to list all the PDBs. Let's try it. But as you can see, it's going to list them way too many times. So if we then instead do for data file in PDB, but we do ls and then the actual variable data file, let's give that a shot. Oops, sorry. Paste. It only gives it to us pretty much the way that we want it. It only lists what we see when we do ls, but just one by one. And this is because here we're specifying that we want to ls the data files. So of course we only have this many data files when I do ls, so it can only list them this many times. Where here it's listing for each specific file that we have, so it's going to print that same file a bunch of times based on the number of files that we have. So yeah, why do these two loops give us different outputs? I'll just kind of explain that. So yeah, this would expand to ls for each one here, and it would go through these loops a bunch of times and print it for each number of files that we have that command for. Whereas here we're assigning the value of data file, and then it's being used for ls. Next up is limiting sets of files. So what would be the output of running the following loop in shell lesson data molecules directory? So for file name in C star, do ls file name. Do you guys think that no files are listed? So if I go back in here, so if we have C and then the wildcard, no files are listed, all files are listed, only cubane, octane, and pentane are listed, or only cubane is listed. Nothing in the chat. So let me just close that. So I'm sure you guys already know how these wildcards work. So of course, it's only going to look at files that start with C and then have that wildcard. So only cubane is going to be listed. Next up, how would the output differ from using this command instead? So for file name in wild type C, wild type do ls file name, done. So would that be the same? Would it list all the files now since we have two wild types? Would it list only cubane, octane, or would it list just octane? That is going to be number 4 again, because even though you're asking for a wild type at the start as well, it will also match 0 characters. So it checks and it knows that, so it can assign 0 to the front, and then it looks for any files that start with the letter C and that end with whatever they want to, and it finds both cubane as well as octane. Please let me know if you want me to kind of go back and do something again, if you've either zoned out or just got confused. But for now, we'll keep moving along. So now we're going to look at the advantages of Glob. So Glob expansion with characters like the wildcard is very fast and efficient. Don't be tempted to use ls to work out what file paths to loop over. It's very slow and inefficient. So for file in ls input, do, whatever. So we're going to look at an exercise of saving to a file in a loop. So in the shell, in the molecules directory, which we are in, what is the effect of this loop? So for alkanes in PDB, echo alkanes, and then cat alkanes into alkanes PDB. So do we have that alkanes file yet? No, we don't. But if we run this, so for alkanes in the PDB, it's going to echo the alkane for us on our terminal, and then it's going to append this value for alkanes into a file called alkanes.pdb. So do you guys think it'll print everything into alkanes? Is it just going to print some specific ones? Is it printing all of these and the text from propane, or none of the above? So the solution here is it's going to be that text from each file in turn gets written to alkanes. So because we're using just one arrow there, if I run this now, so it has echoed all of the alkanes for us one by one. But if we now see that we have alkanes.pdb and we do nano alkanes to have a look at what's inside there, there's only one set of files information here. And that is because it's going to take that last file. Because we only used one arrow, it's going to actually override what we've written each time instead of append it to the bottom. So moving on, doing this exercise of saving to a file in the loop, part 2. So again, in molecules, if we now use what we just had, but instead of one arrow, we're going to pop in another one. So it's again showing us the echo. They didn't use it here, but that's all right. Now we can nano alkanes. And now you can see that we have each file's information. Now if we move into creatures, let's see what we're up to here. So we have a more complicated loop. Echo file name, it'll tell us the file name, and then we'll get the top 100 of that file name, and then we pipe that into the tail function, and this will get the so from 80 to 100 for us. So the shell starts by expanding dat to create a list of files. Loop body then executes those two commands. The first command, echo, prints its command line arguments to standard output. So yeah, if it'd be the same as just doing this, and it prints in the command line interface. So in this case, since the shell expands file name to be the name of a file, echo file name prints the name of a file. Note that we can't write this as for file name and dat file name, because here we've gotten rid of that echo file name, and it's assuming that we're trying to run this variable as some sort of command, and it will not be happy with you. So paste that in here. Oh, we're in the wrong directory as well. So if I move into creatures, basilisks, yep. So yep, if we do that, it has given us the head information, so from 80 to 100 of its genome, but it's saying that it cannot find basilisk.dat because it's assuming that it's some sort of command for us. Is that all good? Yep. So now we're going to deal with some spaces in the names, because usually, especially on Windows, you guys are probably, or Mac, you're probably used to just naming your files whatever space, whatever, just because we're all used to doing that. And I've also gotten out of that habit now since I've been using a lot of Unix. So spaces are used to separate the elements of the list that we're going to loop over. So that's how it does it. Default. So if we have a file, for example, so if we have a file that is called reddragon.dat with a space, or purpleunicorn.dat, to loop over these files, we'd need to add a double quotation around both of those. And it is simpler to just avoid using spaces altogether. Because if, for example, here, Sorry, my bad. So yeah, it's just easier to not use spaces. It's what I usually use is underscores or dashes. So the files above don't exist, so if we run the above code, the head command will be unable to find them. However, the error message returned will show the names of the files it is expecting. So yeah, we don't have those files, but it will show that the names that we're expecting are the full names of the files up there. So if you remove the quotes around the file names, the loop above seems to, in the loop above, to see the effect of the quotes on the spaces, you get a different output. One second. My bad. So, yep, so if you were to remove those quotation marks and then run that same command for file name in yada, let me close that. You would get the loop trying to run through each of those files just based on the spaces in the name. So it will look for red, it goes no file, it would look for dragon.dat, it says no file, and then it also looks for purple. And since we have a file in here called unicorn, it does in fact work on that, and it would give us the genome sequence of unicorn. So moving on from that, copying with glob, we would like to modify each of the files in creatures, but also save a version of the original file. So we won't be able to do just cp wildcard dat and then original dat, because this would expand to every single file that we have that ends in dat, and we'd want to copy that into just original wildcard dat. And when you give CP more than 2 inputs, what happens is that it expects the last input to be a directory where it can copy all the files that you gave it. But instead here, there is no directory named original wildcard dat, so it gives us an error. So yeah, if we check here, that file doesn't exist. If we try running this command, paste, yep, original, so target original wildcard dat is not a directory. Instead, what we want to use is a loop, like we've been learning. So for file name in *stat, do copy file name and then original file name. That way it's going to look at the first file, go, okay, for the first file, I'm going to copy that file name that I have right now into one that is called original dash file name. So if we do that, paste, but again, remove these. And now if we do ls, we have each single individual file as original dash minotaur basilisk unicorn. So yeah, like I said, it runs through one by one. Basilisk to original basilisk, minotaur to original minotaur, unicorn. So this is just kind of, whoops, a workflow of what we did. So if we instead put echo at the front of the copy command, it'll show us what we are going to have as the standard output. So if we start here, do we have a new value? So it'll start with, let's say, unicorn.dat. Yes, it hasn't run through this. It'll run through the process. So unicorn, echo, copy unicorn to unicorn original. And then it comes back because we have a loop defined. Then it'll take minotaur. Is it a new value? Nope. So yes, run the process, comes back, basilisk, yep, and then it comes back and it looks at unicorn again. Is it a new value? Nope, and it ends. Moving on, so Now we're looking at Nelle's pipelines, so processing files. Nelle is now ready to process her data files using goostats.sh, a shell script written by her supervisor. This calculates some statistics for a protein sample file and takes two arguments: an input file containing the raw data and an output file to store the calculated statistics. Since she's still learning how to use a shell, she decides to build up on the required commands in stages. So her first step is to make sure she selected the right input files. So one starting with A or B rather than Z. And in her home directory, she would type cd North Pacific Gyre, my bad, and then the state so she's in this directory now. So for the data file in any wildcard A and B, it's going to echo her the data files. So then her next step is to decide what to call the files that goostats analysis program will create. Prefixing each input file's name with stats seems simple, so she modifies her loop to do that. So she will echo data files into stats data files. So right now she's just checking, because she's using echo, to make sure that when she removes the echo command and actually moves the data files, it's going to come out in the way that she wants them to look. So it's going to change this one into this one. Yeah, so yeah, she hasn't actually run it yet. She's just making sure. But typing in the commands over and over again is becoming tedious, so Nelle is worried, and also Nelle is worried about making mistakes. So instead of re-entering her loop, she presses up. And in response, the shell redisplays the whole loop on one line using semicolons to separate each pieces. So yeah, that's what you might have seen me doing, and you might have also seen Aditya doing. If you click up, it brings up all the commands that you have been running, and you can also click down to move up and down around the command. So yeah, as you can tell, it's now using the semicolons to split up where there would be a enter. Now using left arrow keys, Nelle backs up and changes the command echo to bash. So now instead of just echoing what she wants to happen to these files, she's going to change their names to stats any A or B. So when she presses enter, the shell command runs the modify command. However, nothing appears to happen. There is no output. After a moment, Nelle realizes that since her script doesn't print anything on the screen any longer, she has no idea whether it is running, much less how quickly. She kills the running command by typing Control-C and up to repeat the command, but edits it to read. So for example, if, you're running some sort of program and it's working in your command line interface, and let's say it takes quite a long time, you're going to see it working, or you will just be stuck on kind of you've clicked enter, it's waiting one line down, but your prompt hasn't come back up again, so you're not exactly sure what it's doing. So to stop your current process, you can just click Control-C. So if I can't think of anything that would make my terminal freeze right now, but if I was doing ls and then, or if I've even typed a really long command like and basilisk to, and then halfway through I'm like, oh no, I'd like to do something else, but you don't want to execute that command, you can type Control-C and that will bring you to a fresh prompt. So then she edits it to echo the data file and then bash it. So then it will show her what's happening each time. So now we're going to look at some history, so beginning and end. We can move to the beginning of a line in the shell by typing Control-A and to the end using Control-E. So for example, if I do, let's say for this command, I want to go all the way to the front, but doing this takes way too long, I can just do Control-A, boom, at the front, Control-E, at the back. Control-C, because I don't want to run this command right now, I just want to get to a new prompt, Control-C, I'm back. So when Nelle runs her program now, it produces one line of output every 5 seconds or so. So this is going to take her at least 2 hours. To check, she opens a new terminal, goes to the same directory, and uses cat on her new stats files to examine the output so it looks good, and she moves on. But now there is also another way to repeat previous works, and that is to use a history command to get the last few hundred commands that you have typed. And then you can also use exclamation point and then the numbers, where the 1, 2, 3 is replaced by the command number that you want to repeat. So for example, if I just type history, it will show me pretty much everything that I've ran so far. But for example, if I just want to look at the last few, I can again use history, pipe that into tail-n5, and this is what we were just looking at. And then again, she can run goose stats on any new files that she makes by just typing exclamation point, and let's do 414, that is ls, and that just lists what we have here, since we're in the same working directory. So there are a number of other shortcuts that you can use with history. Control-R, reverse, Control-R one or more additional times to search for earlier matches. So these are just a bunch of different things you can do. Exclamation, exclamation retrieves the immediately preceding command. You may or may not find this easier than just using your up arrows. Retrieves the last word of the command. And sometimes that can be useful to, I guess, just, again, pressing up, although I find that it's most useful to just use up and down keys. And moving on. So doing a dry run, a loop is a way to do many things at once, or to make many mistakes at once. And I sure have made many mistakes by running a loop script. One way to make sure that your loop is doing what you want it to do is to use the echo command, like I said before. And suppose we want to preview the commands. The following loop will execute without actually running the command. So for data file in PDB, we want to cat the data file, so append the contents of data files into a file called all.pdb and append it below each existing set of data that we've already put into the file. So what is the difference between the two loops below, and which one would we want to run? So for data file in PDB, echo cat data file into all, or would we want to do echo in quotations data file to all? Just moving along quickly. The second version is the one that we want to run. This prints to screen everything enclosed in quotation marks, expanding the loop variable name because we have prefixed it with a $sign. It also does not modify or create the file all, as the two arrow signs are treated literally as part of a string rather than as a redirect instruction. So in the first version, it will append the output of the command. So it will still do this bit to the file. So yeah, you can go ahead and try it, but I think we're just going to move on for now. So for nested loops, suppose we want to set up a directory structure to organize some experiments measuring reaction rate and constants with different compounds and different temperatures. What would be the result of the following code? So for species in Cubane, let me move into that directory. So cd molecules, ls, for species in Cubane, ethane, methane, for temperature in 25, 30, 37, 40, do make directory species temperature. So if we copy that, right now we can see that we only have alkanes, ethane, octane, propane, cubane, methane, pentane. If I paste this in and do ls, you can notice that we now have cubane with the numbers 25, 30, 37, and 40 made as directories, as well as for each other molecule that we've given our script. So for each species in here, we're going to append 25 to the end there and create that as a directory. And we're going to do that for each molecule. So yeah, it iterates over both lists twice and makes all of those directories for us. So that's pretty useful. So now to recap, a loop repeats commands once for everything in a list. Every for loop needs a variable to refer to the thing it is currently operating on. Use a $name to expand a variable, for example, to get its value. You can also use it in curly brackets. That is going to do the same thing for you. Do not use open spaces, quotations, or wildcards such as asterisks or question mark in file names, because it will cause you a lot of pain. So try to just use numbers, words, underscores, dashes. Those are usually best. And yeah, give files consistent names so that you don't get confused, and that the wildcards patterns make it easy to select them for looping. Use the up arrow to scroll through previous commands. You can use history to display recent commands and number to repeat a command, and use Control R to search through previously entered commands.